All right, so today we are looking at Unit 1, Lesson 5, and what our sort of focus for today's lesson is something called the recursive form or the recursive definition of a sequence. And what the recursive form or recursive definition is, it's essentially a formal notation that we use for a sequence that says how we produce a new term based on the previous term. Now, we've talked about this before. We've talked about kind of informally, if we know the pattern and we know the starting terms, how we can produce a new term based on the previous term. But now we're actually going to use formal function notation. Notice, for example, like for the starting term, which we usually refer to as term 0, notice we're going to use the notation f of 0. And that's going to be our starting term. The recursive definition actually has two parts. It has the starting term, f of 0, and then it has how we produce a new term based on the previous term. Now, this will make a little bit more sense when we actually look at the examples, and I actually do an example. So let's do that. Here are examples. So for each sequence, we're going to determine whether it's arithmetic, geometric, or neither. And then we're going to write both parts of the recursive definition based on our lesson notes. So if I look at number one, I have 30, 40, 50, 60. It's pretty clear that I'm adding 10. The pattern is to add 10 each time. So that's going to make it an arithmetic sequence. I'm just going to abbreviate that. So number one, it's an arithmetic sequence because we're adding 10. Now that's important that we recognize the pattern because now we're going to write both parts of the recursive definition of that sequence. So the first part is what's our starting term? So our starting term of the sequence is 30. So the way we're going to write that is f of 0 equals the starting term, in this case, 30. Okay. And then the second part, which actually talks about how we produce new terms based on the previous term, is simply going to be one of these three. Now, we've already determined that the pattern is adding 10. So we're going to write it just like this. So we're going to write f of n equals f of n minus 1, just like we have here, f of n equals f of n minus 1 plus the number, in this case, plus 10. These two things right here make up what we call the recursive definition. It tells us what our starting term is. And again, we're using formal notation, formal function notation. So f of 0 equals 30. And then it tells us how we get new terms based on the previous term. So what this says, f of n means the new term is equal to the previous term, f of n minus 1, the term prior to it, but you add 10 to it. So this is our recursive definition. Okay, let's look at number 2. Okay, number 2, 80, 40, 20, and 10. Okay, so once again, we're decreasing. It looks like we're dividing by 2. So this is going to be a geometric sequence. Okay, and our common ratio in this case, we're dividing by 2. So our common ratio is, is 1/2 because we're dividing by 2. Okay, so the first part of our recursive definition is going to be f of 0 equals a number. Okay, so in this case, f of 0 equals our starting term. Our starting term in this case is 80. So f of 0 equals 80. And then this time, because it's a geometric sequence, we're going to use this one down here because our pattern is to multiply. So it's going to be f of n equals f of n minus 1 times, and what did we say we were multiplying by? We were multiplying by a half. So this right here is our answer for number 2. Okay. Let's do number 3 now. 20, 13, 6, and negative 1. It looks like we are going down by 7. 20 minus 7 is 13. 13 minus 7 is 6. 6 minus 7 is negative 1. So this is an arithmetic sequence, and our common difference is going to be negative 7 because we are multiplying by 7. Okay? So if we continue here, our f of 0, our first term for number 3 is going to be 20, since that's our starting term. And then we are going to use this one now for the second part because our pattern is to subtract. So f of n equals f of n minus 1 minus 7. And that's our answer for number 3. Number 4. Excuse me. Number 4, it looks like we are doubling. 1 times 2 is 2, times 2 is 4, times 2 is 8. So this is a geometric sequence. Our common ratio is 2 because we're multiplying by 2 each time. So our f of 0, our first part, f of 0 is going to be 1. And our f of n, now we're going to use the multiplying one again. So that's the one at the bottom. So it's going to be f of n equals f of n minus 1 times 2. All right, hopefully we're getting the hang of this, but let's do number 5. All right, number 5 is a little tricky. We're still starting with 1, but it looks like we're multiplying, we're halving at every time. We're dividing by 2 because 1 divided by 2 is a half, and a half divided by 2 is a quarter. So this is indeed a geometric sequence, and because we're dividing by 2, my common ratio is a half. So my f of 0 is going to be 1, just like number 4. But now the second part is going to be f of n equals f of n minus 1. But instead of times 2, it's going to be times a half. All right. And let's finish it off with number 6. All right. Number 6, it looks like we're tripling. So this is going to be a geometric sequence. And our common ratio, is 3. Okay, because 3 times 3 is 9. 9 times 3 is 27. 27 times 3 is 81. So my f of 0, my starting term, is going to be 3. That's my starting term. And then when we write the second part, it's going to be f of n minus 1. Actually, I screwed up there. It's going to be f of n. Okay, so we're going to use this one right here. F of n equals f of n minus 1 times 3, because our pattern is to multiply by 3 every time. Okay, so your cool down tonight will be a few examples just like this.